Hi all again. So in this video, we visualize elliptic and hyperbolic coherent structures from using single trajectory diagnostics. So the advantage of using these single trajectory diagnostics, such as the TRA, so the trajectory rotation angle, and the TSE, the trajectory stretching exponent, is that they tend to approximate features, for example, from the FTLE or the LEVD, using just individual trajectories. So for example, in the FTLE, of course, we had to compute the gradient of the flow map. So this required actually in 3D using 6 auxiliary trajectories to compute the FTLE value for one initial condition. Now, using the TSE, one can approximate features from the FTLE, however, which with much fewer trajectories, namely just one. So it's a computational speedup. It's a substantial computational speedup, actually. And the same also holds for the TRA and the LEVD. You will see that the TRA and the LEVD will show strikingly the same features, however, at a with much less computational burden, of course. So let's take a look at, for example, the TRA. Now, I want to make clear that the TRA and the TSE, they are, first of all, the same types of functions that we use in the 2D case. So if you take a look at the TRA in 3D, the formula for computing TRA in 3D is exactly the same as in 2D. So you simply take computer trajectory, you take velocity along the trajectory, and the TRA is simply the angle between two subsequent velocity vectors, and then you simply take the average along this trajectory. Same thing also holds for a TSE. So if I go back to the TSE, then the TSE also, you basically take, so there are of course two different ways to define the TSE. So one is the classic trajectory stretching exponent, and one is the average trajectory stretching exponent. So the original trajectory stretching exponent simply takes the final velocity and the initial velocity, computes the ratio of the absolute value of those, and then simply takes the logarithm. And then there's also the average stretching exponent, which is used to highlight general hyperbolic features. And there you simply take two subsequent velocity vectors, compute the norm of the two, take the ratio, the logarithm, and then you simply average this along a trajectory. So this is the same stuff that we had in the 2D case as well. So if we now take a look at, for example, the TRA on the steady BC flow. Why do I just use a steady BC flow? Well, because both the TRA and the TSE, they only approximate features of the FTLE or the LEVD if the velocity field is slowly varying. So basically, whenever the partial derivative of the velocity field compared to the advective term of the velocity field, of the velocity is much smaller. So hence the ideal setting is of course that you have a steady velocity field. So that's the ideal setting, and that's why we use the steady BC flow. So if we take a look now at the script on TRA, let me run this actually so that it nicely visualizes. So we have, of course, the steady BC flow, the classical one, with the following parameters. We start by importing the data, which is stored in this folder, as always. We define computational parameters, such as the number of cores, whether the flow has periodic or non-periodic boundary conditions, and whether it is steady or unsteady. Then we need to define a spatiotemporal domain. So what we do here is, of course, the domain which we specify, since we're dealing with the ABC flow, it is natural to consider the 6 faces of the cube. And since the opposite face of the cube are exactly the same, we will just compute the TRA for initial conditions on the XY plane. So on the XY plane, on the XZ plane, and on the YZ plane. This is basically the same as also in the FTLE or LEVD computation. And then, of course, we compute the TRA by first computing the velocity along trajectories over some finite time interval, and then we simply pass this velocity rate to the TRA function, which then returns to each initial condition a certain TRA value. Finally, since these are sparse data diagnostics, one can also test its ability to visualize elliptic flow structures, in this case here for the TRA, under progressive and random subsampling. So we will take away some random initial conditions. We will reconstruct the TRA field and see how it performs for the steady BC flow. So again, the computations here have all been parallelized. So I've been, for example, taking the initial conditions on the XY plane. I vectorized them. I put them into different batches. And then I computed the TRA for all of these initial conditions. This step here simply made sure to reshape the TRA, not anymore in a vectorized form, but on a mesh grid. The same is done also for the XZ plane, where the only thing that changes is basically this part here. Of course, the XY plane is defined by the Z equals 0 cross section. The XZ plane is defined by the Y equals 0 cross section, and the YZ plane is defined by the X equals 0 cross section. We can then plot this and visualize it as a cube, and you can see that the ability to visualize these main vortices is pretty good also in the TRA. And keep in mind that here we just use single trajectories. So it's of course, it does not exactly reproduce the features of the LVD, because in the LVD, this main vortex here was much stronger, but still it is visible also here in the TRA. And especially these two major ones are also clearly visible. Then this is the same, just plotted for the individual cross sections. And one can then test its ability by randomly subsampling the TRA. So I here just took away initial conditions randomly. Of course, the plot gets a bit worse. It gets a bit more blurry, but still the two major features here are still retained. And one can proceed by further subsampling. So now I'm just taking 1% of the initial trajectories. So if initially I had 400,000, and here I'm just taking 1%, which means that I went from 400,000 to 4,000, which is a major subsampling, and still you can see the two major features here are fairly well visualized. Now, what happens if I further decrease? So I go to 0.1% subsampling. Well, interestingly, of course, it depends on how lucky you are, because you always, so if these two features are still sampled, then of course they will be clearly visible. Now here, of course, this feature is still visible even under 0.1% subsampling. And this feature here is actually also still pretty visible. Of course, not as strongly. This is not to be expected because we're massively subsampling, but it's still fairly well visible. This is for the TRA. Now I can show you through the TSE script, which is exactly the same. The only thing is that instead of the TRA, we have now the TSE. And we basically compute both the TSE and the average TSE. And here we should actually have TSE and not TRA, of course. And if we take a look at now the results, then we have here, okay, this is the TSE, which is, of course, not as clear as the FTLE. It's not to be expected. However, it's still, I would say, highlights fairly well some hyperbolic structures here. Now, if I use a different color map, it gets even more visible. So, for example, the white areas indicates areas of compression, so of negative values, whereas the red spots indicates area of stretching. Actually, if we take the TSE bar, so the average TSE, the structures are actually even better visible. So actually there are still some footprints of these vortices also by the TSE, but if you take a look at these hyperbolic flow features, they're much better captured than in this TSE here. And if you take a look at now with this color map, you can really see that you can see these ridges here of the TSE bar, which of course they are not as precise and as accurate as the FTD ridges. However, they are still related to the FTLE values mathematically for steady flows. One can then also start by progressively subsampling, and that's actually where the strength of the TSE is clearly shown, because if you start to subsample the FTLE value, then you will get rubbish, because subsampling FTLE means that you need to compute derivatives over larger distances and they become fairly inaccurate, whereas here you do not need to compute any spatial derivatives. And still you can see that the major hyperbolic regions are fairly well captured, especially here and here. and there is still a pretty strong indication of the vortices. One can then actually further proceed to subsampling, and you can see that there is still this major hyperbolic flow region, which is still visible, also with such strong subsampling. A similar behavior is not to be expected in the FTLE. With that, I conclude the section on the single trajectory diagnostics, and in case you have any questions, just feel free to contact me. The important thing is that this TSE, they only make sense if the velocity field or if the vector field that you have is slowly varying. Otherwise, they have no mathematical relationship to the FTLE. The mathematical statement only holds for slowly varying velocity field. That's absolutely important to keep in mind here.